Hi, and welcome to this presentation about mining constraints regions of interest. So, the motivation of this work is that there is more and more spatial temporal data available to us, and we need a way to process them efficiently. One way to do so is to use semantic trajectories, which are easier to reason about. So, the aim of this work is to propose a method to extract semantic element like work or movie theater from the raw trajectories. The general approach is the following: we divide the map with a grid and we assign a density value to each cell of the grid. A cell is said to be dense if its density value is above a given minimum density threshold. As density function, we use the number of crossing trajectories in each cell. Then we express the region of interest as an aggregation of the dense cells. As an example, you have on the left an initial set of dense cells on the city of Porto, and on the right you have the solution found by our method. And you can see that we extract the train station, some popular highway exit, and the historical center of the city. Before going into the detail of our method, I will present popular region, which is an existing method to extract a region of interest. So you have your grid with the gray cells that are dense, and you select the cell with the highest density not already in a region of interest. The idea is to extend this from this cell to create a rectangular region of interest. So the extension can be done in any of the four directions, but you have some constraints. First, you cannot extend on no dense cells, so you see that if we would extend on top EC, we would have no dense cells, so we cannot extend in that direction. We cannot extend also in an area which is already in another region. Okay, that is forbidden. So then you extend in a direction that gives the highest average density. Then the second constraint is that you cannot extend on an area such as after the extension, the rectangle would have average density below the minimum density threshold. And you continue until you cannot extend in any direction, and you repeat this process with the other dense cells. So this is the result on the previous set of dense cells I showed. You see that there is a big rectangles at the center of the city because the cells in that area are very dense, and you can easily connect the different parts in the extension process. So this algorithm is good, it's scalable, and for most configuration it gives very good and intuitive results, but you have no formalization of the output. You can only produce rectangular regions, and you cannot accept easily background knowledge from the user that might want its region in with certain constraints. So now our method. We consider the region of interest as an encoding of the density of the cells in the grid. So for example, here you have two regions, two rectangles, and we say every cell in the rectangles are dense, and every cell outside the rectangles are not dense. But obviously this is not true. Okay, you have one dense cell that is not covered by the rectangles, and four dense cells non-dense cells that are covered by the rectangles. You want to find an encoding with as few errors as possible. Okay, but the catch is that it's always possible. So here you have 6 rectangles, and the model makes no error. Okay, but it does not represent well the initial distribution of the cells in the grid, and it's not assumption that we want. Okay, so how to avoid such pathological results? We can limit the number of regions we find, but setting the limit is not trivial. To do so, we use the minimum description length principle to automatically select the number of regions. The MDL principles tells us that if you have multiple models to choose from, for example, the model with 2 or with 6 rectangles, then you should select the model that compresses the most data. So in terms of the MDL principle, you have the length of the model, you have the length of the data given the model, and you want to minimize the sum of the two, so you have this trade-off between the complexity of the model and the generalization of the data. In our case, we work with integers, so the length of the model is just the sum of the length of the region of interest in the model. So a rectangle needs 4 integers, and a circle needs only 3 integers. and the length of the data given the model is just the number of errors the model makes, times 2, because you need 2 integers per cell. If we take back the two previous models, we see that we prefer this model because its description length is lower than that model. So the overall method is the following. We generate a set of candidates, and then we will select from this set of candidates the set of region of interest to return to the user. In the set of candidates, you can have any shape. You are not limited to the shape, and you apply per region constraint. For example, if you want every region in your solution to have at least one bus stop, you do not add to the set of candidates all the candidates that do not have at least one bus stop in them. Okay. And then in the ELP, you can model constraint between the region of interest as long as it can be expressed with linear constraints. So the ELP is the following. So you have one decision variable xi per candidate, and the weight of each candidate is its contribution to the description length. Okay, so you have here the description, the contribution to the error of the description length, and here the contribution to the length of the model, to the description length. And you minimize the sum of the contribution to the description length, which gives the minimization of the description length of the model. Okay, and then here you have the non-overlapping constraint that tells us that for each cell you should select at most one candidate that cover that cell. Some experiments now. So we have two versions of our method, with rectangles and with rectangles and circles. And we compare our method with popular region and optics. So, as expected, popular region has the best runtime of all methods. And you can see on the two first rows that the optimization time of our method is mainly determined by the number of candidates in the ELP. And as soon as the number of candidates become reasonable, our runtime becomes reasonable, even comparable to optics. Now, some words about the description length. So, on the left, you have the number of integers needed to encode the errors of the models, and on the right, you have the number of integers needed to encode the model. And so you can see, as we said on the left, that for small minimum density threshold, popular region have a high number of errors, but as soon as the minimum density threshold increase, its number of errors drop, and our method makes more error. This is due to the fact that we do not cover every dense cells on the grid. And so if they are isolated dense cells, our method will ignore them, consider them as no's. But on the other hand, our method always produces smaller model to encode with less regions of interest. And you can see that it tends to 0 because when there is not a lot of dense cells, it is considered no's by our method. In conclusion, we proposed an optimization model to extract region of interest from trajectory data. And this method is flexible because it allows the user to add a wide variety of constraints in the model, constraint on the region of interest and between the region of interest. The runtime for the ELP becomes reasonable as long as the number of candidates is not too high, which should be the case if we are in a very constrained applications. The code is open source, you can check it out if you want. And the next steps for this work is either removing the grid or using the density information inside it and provide support for more complex constraints. Thank you for your attention.